I want to illustrate why the power of artificial intelligence in modern architectures is so unexpected, even unreasonable, using a series of examples that I call disanalogies, paradoxical analogies that show how what we expect in the physical world doesn't correspond at all to what happens in the world of AI. I start from a slide that Jensen Huang, founder and CEO of NVIDIA, presented at the Consumer Electronics Show in January 2025. In this slide, he shows how scalability laws apply in successive waves across the different phases of the development and application of modern artificial intelligence engines. Each of these laws develops exponential power, and it's the envelope of these various scalability laws that we observe in the increasingly powerful applications we use every day. What happens when we train the engine? We would expect to maximize AI power as we would the speed of building a bridge. If it takes 1,000 people to build a bridge in 1,000 days, is it reasonable to expect that 1,000,000 people could build that same bridge in just one day? Paradoxical, right? Yet that's what happens in AI systems. Or if we want to squeeze the system to produce intelligence and we keep squeezing more and more, it's a bit like squeezing a lemon that produces a certain volume of juice and deciding, no, let's squeeze it longer. And after 10 hours, we discover that a single lemon has produced 1,000 times the juice. This is what happens in AI, where we manage to extract more intelligence juice by training longer. When the system is trained, it is balanced so that its characteristics allow certain yields across different application areas. It's then possible to intervene with what is called fine-tuning, specializing the model in a particular area to highlight capabilities that were previously latent but not sufficiently accessible or developed. It's a bit like what we see every day. You give your car a new coat of paint and gleaming it starts to fly, right? The car's latent capacity, which no one presumed, manifests itself. It's not only shiny, but it flies too. Or knowing that 10 new guests are coming to your house. You don't worry, because the house develops rooms that weren't there before, where you can accommodate them. And if 1,000 arrive, that's fine too. More recently, we have begun to introduce models that are able to adapt their behavior, not during training, not during fine-tuning, but during execution, through the dialogue with users and even with itself, where the system can be invited to reflect on what it does, focusing more. Perhaps that's what happens when you decide that faced with a particularly complicated problem, the right thing to do is drink 1,000 cups of coffee, because this will allow you to focus better and support the necessary reasoning. And no, that's not how our brain works or our physiology, but it is exactly what happens in artificial intelligence systems. The sum of these unexpected and unreasonable scalability laws, which we continue to discover, represents a generalization of Moore's law, a generalization of the approach expressed and analyzed by Ray Kurzweil in his law of accelerating returns. And it's fantastic to be able to take advantage of it. Just as in the past, when those who said Moore's law was dead were wrong, because the creativity and passion of engineers worldwide have allowed it to continue through increasingly different and innovative approaches, so it is today, when those who claim that AI is already finished, that this wave is running out, don't realize they are looking at a single exponential curve instead of recognizing the jolting paradigm, the envelope of curves that outline the innovation we will continue to explore.